Hey everybody, welcome to part 6 of the course, Relativity. So what we're going to do in part 6.1 is we're going to talk about what we mean by observers in relative motion, what we mean by a relativity theory, how light is involved in the relativity theory, and what are some of the consequences of this relativity theory once we factor light into the model. And this theory of relativity that we're going to be looking at is called the special theory of relativity in part 6.1, developed by Einstein. And it has some interesting consequences, predictions about time and length in particular, that have experimentally been confirmed. Very strange behavior indeed. So we'll look at that. We'll continue in part 6.2 to talk about some consequences of the special theory of relativity in terms of mass and energy. Again, some really neat consequences. But then we're also going to discuss another theory of Einstein's that he developed that's usually called the general theory of relativity, which is really a statement about gravity. But we'll see that light is also involved in the general theory of relativity. And then we'll end and discuss what are the implications of these theories when it comes to time travel. Okay, so that'll be a fun way to wrap up the course. Okay, so let's go ahead and get started and talk first about what we mean by relative motion and a relativity theory. So we have to define some terms that we're going to use, and one of those terms is an observer. So an observer is simply someone who measures some physical quantity. That quantity can be a position, for example, or time, or speed, acceleration, force, okay? Now, when an observer measures a quantity, they're going to use their own what we call coordinate system for measuring position and their own clock for measuring time. So think about if you're going to measure the position of an object, you're going to say, okay, I'm going to have some reference point. We usually call that the origin, right? If we're going to make a sketch of axes. And then we actually do draw lines representing the axes, right, of our coordinate system. So we live in a three-dimensional spatial world, at least that's the way we observe it. So we would draw one line and call that the x-axis, another line perpendicular to that one, call that the y-axis, and then a third line perpendicular to the first two that we call the z-axis. So I could say, okay, this object occupies this position by giving x, y, and z, right, relative to the origin. And then I could also say, you know, and it occupies this position at some time t, measured on my clock. And then if the object moves, I can record changes in position, right? And I can get speeds and then accelerations and all the other physical quantities. Okay, so that's what we mean by an observer. An event is just something physical that occurs at some position at some time. Okay, so it could be anything. As I say here, it could be a light going on or a light going off. Or it could just be there's an object at some point and you measure that, okay, that position in time. Because yes, the object was there at that position and at that time. So events are measured by observers, okay? So that's the jargon that tends to get used in relativity theories. Okay, so what do we mean by relative motion then? So two observers are in relative motion if the distance between them is changing. That's the key. Okay, so that's the only way they're going to be in relative motion. Now, the distance can be getting smaller or larger. So the observers can be getting closer together or getting farther apart. They're going still to be in relative motion. One observer can be moving, or both could be moving. Okay, so one could be stationary with respect to us, and the other could be moving. Or both could be moving, relative to us, but they have to be moving, if they're moving in the same direction, they have to be moving at different speeds. If they're moving in opposite directions, they're going to be in relative motion, even if they're moving at the same speed, because the distance between them is changing. But if they're moving in the same direction, they can't be moving at the same speed, because if they did, then the distance between them wouldn't be changing. So we would not call that relative motion. Okay? And then I have I just drew some examples because it was fun to draw them. So I think I looked at every possible example. You could have one observer stationary with respect to us and one moving to the left, right? So they would be in relative motion as long as that observer is moving to the left. Or one stationary, one's moving to the right. The other observer stationary, the first observer is moving to the left. Or the first observer is moving to the right. Or both are moving towards each other. Or both are moving, as you see here now, away from each other. Okay? Both could be moving to the left, but they'd have to be moving at different speeds and the same for to the right. Okay? Now, I didn't put this in a slide, but I'll just jot this down. So this is what we mean by relative motion. And what a relativity theory does is it relates with equations, but it relates the physical quantities measured by observers in relative motion. So in other words, one observer could be measuring the position of an object, the velocity of an object, the acceleration of an object, the momentum, the force applied by the object on another object, right? The amount of energy an object has, kinetic energy. So one observer is measuring all these things for some object, yes? The other observer is also measuring the quantities for the same object. What a relativity theory will do is will relate those quantities to each other. So how does the velocity measured by one observer for that object compare to the velocity measured for that object by the other observer, right? That's what a relativity theory will do. So even before Einstein came along, we had a relativity theory that would relate physical quantities. It's sometimes called Newtonian relativity theory from Isaac Newton. So yeah, we could compare. So as an example, I'll give you an example of Newtonian relativity. Relative speeds of moving objects, right? Observers in relative motion will measure different speeds for the same object. That is a consequence. Well, we see that in nature, but it's also predicted and described by Newtonian relativity. Okay, so, and this happens all the time. We're usually not aware of this because we don't really measure the speeds of objects all the time, right? We don't go around saying, oh, that bird's moving at 20 miles per hour. Oh, that car's moving at, right? So we're not measuring those speeds, but it is true if you think about it. Here's an example. Imagine this. Suppose that one observer, I called this observer Jack, is stationary, standing on the sidewalk outside campus, right? Relative to us, maybe we're standing with Jack, okay? So relative to us, Jack's stationary. Jill is in her car and she's driving down the road, driving down Central Avenue at 35 miles per hour, and we'll say to the right. We'll call that direction to the right. Now suppose there is a bird flying also, right, relative to Jack, to the right, in the direction that Jill is traveling, and Jack measures the velocity of that bird to be 5 miles per hour towards Jill. Okay, so you got it? So this bird, relative to Jack, is moving at 5 miles per hour to the right, and relative to Jack, Jill is driving in her car at 35 miles per hour to the right. The question is, if you ask Jill, do you see that bird? She said, yes. How fast and in what direction do you see that bird flying? Okay. Now think about that. See if you can figure that out. How fast and in what direction does Jill see the bird flying? Well, it's a little bit weird Because we don't normally think about this. I mean, Jill looks in her rearview mirror, right, and sees the bird, but probably doesn't really think about how fast is the bird traveling and in what direction, but we're going to ask her. So first of all, realize, right, that relative to Jack, Jill's going 35 to the right, the bird's going 5 to the right. So this bird is going to be traveling at 30 miles per hour relative to Jill. Okay? But here's I don't know if it's the weird thing, but an interesting thing. Notice, though, that since Jill is traveling faster than the bird, the distance between Jill and the bird is getting bigger and bigger and bigger. So Jill looks in the rearview mirror. It's going to look like the bird is going to the left. Jill's going to see the distance between them getting larger and larger. Now, I know what you're thinking. You're like, yeah, but wait, Jill knows she's in the car pulling ahead of the bird. But no, just imagine that Jill is viewing herself as stationary in her own coordinate system, at her own origin, if you will. Relative to that origin, the bird is definitely traveling to the left relative to that origin. Okay, so Jill is going to see definitely a different speed for the bird than Jack measures, but also a different direction. Okay, now again, this is predicted by Newtonian relativity, that relativity theory. In fact, you can write down an equation for what's called the velocity transform, and it would look like this. I'm going to jot this down, and I'll just show you how this works. Again, you don't have to remember this formula, but I just want to show you. I'm going to write it like this. U prime equals U minus V, and I'll explain what those are. Okay, so V here is the relative velocity between Jack and Jill. So V here is the 35 miles per hour, okay? U is going to be the velocity of the bird measured by Jack. So U is going to be plus 5 miles per hour. Now, the reason I'm emphasizing the plus is that plus means to the right for the observer. A minus sign would mean to the left. That's why I'm calling these velocities, because they have not just speed information, but also direction. Okay, U prime is going to be the velocity of the bird measured by Jill. So according to this equation from Newtonian relativity, U prime is going to be U, which is plus 5, minus V, which is 35, and you get negative 30 miles per hour. Now, what that minus sign is telling you is that relative to Jill, that bird's moving to the left. It's facing her. It's not like she sees the tail of the bird in her rearview mirror, right? She sees the face of the bird, but it looks like the bird, in fact, is flying backwards, if you ask Jill. Okay? So that's what that minus sign means. And here's the 30 miles per hour that we said earlier. Okay? So this equation works. In fact, look, let's try this. Oh, I'll waste even more of your time. No. Watch. Let me, I'll change the color. Ooh, let's do purple. Okay. Hey, let's suppose that the bird, instead of going to the right at 5 miles per hour relative to Jack, suppose the bird's going to the left at 5 miles per hour, okay, relative to Jack. So, imagine the bird turns around and it's flying towards Jack at 5 miles per hour. How fast and in what direction would Jill see the bird traveling if she's still going to the right at 35 miles per hour? Well, now the distance between Jill and the bird is getting bigger, but it's getting bigger at a faster, right, at a faster rate than it was when the bird was flying towards her. So I think she's going to see it definitely going to the left, but she's going to see it going, I think, at 40 miles per hour. And that is predicted by this equation right here. Because now what you would do is you would say, okay, U is negative 5 miles per hour, because relative to Jack, the bird's going to the left, so I'm going to put this minus sign here. So now when you go to find u prime, you would do u minus 5 minus v minus 35, and you find out that u prime is negative 40 miles per hour, which means that Jill observes the bird to be going to the left at 40 miles per hour. Okay? So this works. Here's another thing that might help you. Suppose you're sitting in class, right? And I'm standing there and I throw a marker at you. Yes, so I'm throwing the marker at you and you will measure, right, a certain speed as it's coming towards you. What about if I start running towards you and I release the marker with the exact same release speed relative to me that I released it at when I was just standing there? Well, see, now, once that marker leaves my hand, you're going to see it moving faster than before, because it has, before I let go of it, it already has my velocity because it's in my hand. So it's already traveling towards you at my velocity. And then when I give it that throwing force, I give it even more speed. So you're going to see it traveling even faster. But relative to me, that marker leaves my hand with the exact same speed, whether I'm stationary with respect to you or whether I'm moving, okay? And that, again, is predicted by Newtonian relativity. So I just want to establish that observers in relative motion will definitely measure different speeds for the same object, okay? We're not going to worry about all the other quantities, how they compare. I'll just tell you that Newtonian relativity has equations for position, acceleration, force, energy, okay? All right. Oh, another thing, though, I do want to establish about Newtonian relativity, and again, this is the relativity theory that we are used to, is that time is what we call universal. So in other words, right, in fact, the equation to transform time from one observer to another observer is that t prime equals t, which means observers in relative motion all measure the same times. All clocks run at the same rate in Newtonian relativity, and this is what we're used to in our everyday existence. Okay, well, maybe that sets the stage for some weird things that are about to happen. All right, so everybody was happy with this, but Einstein started thinking about some things. And in particular, what he started thinking about was the speed of light. Because it turns out that this speed of light in free space, c, 3 times 10 to the 8 meters per second, it is actually predicted from a series of equations, laws, that are called Maxwell's equations. In fact, I mentioned Maxwell when we were talking about the wave theory of light back in part 5, when I said this new theory of light, this photon model, was challenging the established wave model put forth by some scientists. One of them was Maxwell. So from Maxwell's equations, the speed of light in free space is predicted to be 3 times 10 to the 8 meters per second. But this is a little bit strange that you get a speed predicted from equations, because Newtonian relativity says that the speed of objects, right, is different for observers in relative motion. So this speed that pops out, that's relative to who? What observer measures 3 times 10 to the 8 meters per second? Because it seems like if you got two people in relative motion, they're both not going to measure the same speed for light. So it was weird, Einstein thought, that this speed just popped out. And this is the only time that you get this speed popping out for some quantity like that. In all the laws and things that we have. And the fact that it was pure energy also had Einstein scratching his head, that this speed of light was predicted to be this, but again, relative to who? All right, so a very long story made short. What Einstein finally concluded is very strange, but what he concluded was all observers, as you see in this box, all observers regardless of their relative motion, measure the same speed for light. And this is only true for light. Any particle, any object made out of matter, this is not true. Then you need a relativity theory to compare speeds measured by observers in relative motion. But all observers, no matter how fast they're moving with respect to each other, will measure c for light in free space. It is really strange the more you think about it. Here's that special value, right? And here's an example, right? Just to make you scratch your head. So Jack is standing on the sidewalk, yes. Jill is driving down the road at 35 miles per hour relative to Jack, just like before. But instead of having a bird, right, fly towards Jill relative to Jack, what we now do is Jack has a laser pointer and fires his laser pointer towards Jill. Now he measures the speed of that light to be c. How fast does Jill see the light coming towards her? Well, if that was a bird, we know the speed would be different. But if it's light, guess what? She also measures it to be traveling at c. I don't care how fast she's traveling. She'll measure that laser light to be traveling at c. That is strange. This is even, maybe makes it even seem more strange or stranger. Suppose Jack is on a moon base. You can't see him, but Jack is here on this moon base, right? Jill is in her spaceship zooming towards the moon at 0.99 c, 99% the speed of light. She's flying in from a different solar system, right? Coming in. Jack sends a laser signal to the ship. So Jack shoots a laser beam from the moon base towards this ship. He measures that speed of light to be c. How fast does Jill see the light coming towards her? It's still going to be c. And that is so strange. I mean, it seems like if she's approaching this really, really, really fast, and this is going to the left really, really, really fast, that she should see the light coming even faster than Jack sees it. But nope, she will also see the light traveling this way at speed c. Okay, this is sometimes called the principle of the constancy, this fancy term, the constancy of the speed of light. The constancy of the speed of light. So this is what Einstein assumed. And by the way, this is not predicted by Newtonian relativity. By the relativity theory that we're used to, observers in motion should measure different speeds for light. But it turns out, as far as we can tell, Einstein was correct. The constancy of the speed of light is correct, which means Newtonian relativity has to be fixed. It has to be corrected. And that's what Einstein did. Okay? All right. In the next video, then, we're going to look at some of the consequences of Einstein's theory, which we call the special theory of relativity, which is a patch, if you will, to Newtonian relativity. There's nothing wrong with Newtonian relativity, it turns out, if observers are not in relative motion at super high speeds. We're talking near the speed of light. So as long as the relative motion between two observers involves speeds that is much less than the speed of light, Newtonian relativity is fine. And since the speed of light is such a huge number, Newtonian relativity is fine in almost every case. It's only when you have things traveling near the speed of light, which means it's only going to be tiny particles. We can only get tiny particles like electrons, protons, neutrons to travel near the speed of light. And we can only do that at certain facilities, so-called particle accelerators. But it's still neat to talk about these effects because they are real effects that do occur when relative speeds are near that speed of light. Okay, and we'll look at that in more detail in the next set of videos. Okay, bye-bye.